alternate delivery. And then we'll dive into the actual method that was selected and a little bit into design and construction. All right, go ahead. All right, so the Columbia Boulevard wastewater treatment plant serves over 500,000 people, dry weather flow, pretty big, 110 MGD, wet weather, 450 MGD, started in 1952, and that actually plays into the project because it's grown and morphed ever since. So this isn't a 110 MGD plant that was built from scratch, and so it's all nicely laid out. It's a treatment plant that's been adjusted, modified through projects and probably just O&M. And so it's not a clean cut treatment plant. Now, what you see in red over there on the photo is the area where the project occurred, and it's the wash water project. So that's piping that's down in the tunnels underground. So big treatment plants like this, you don't bury your pipes, you build tunnels, and because you got so many pipes. And some of those tunnels are 30 foot by 30 foot, and others are a lot smaller. We had one on this project I called the vanishing tunnel, because in the beginning, not only could you stand up straight, but the ceiling was 10 feet above you. And by the end of the time you got to the end of the tunnel, you were bent down double, literally, to try to walk through the tunnel. It just kept getting smaller and smaller and smaller. So that's where the project occurred. So in the beginning, this started in 2014 as a small projects on call, which Tetra Tech had that contract at the time. And what this was 600 feet approximately of 12-inch wash water pipe, which is, it's not potable water, it's not effluent, it's just untreated water that they use in the process. And it's down in the tunnels and it's corroded to beat the band. You'll see that later. And they wanted to replace it. Okay, Hunter. So immediately we saw some challenges. One of them was it's an incredibly corrosive environment. In that middle photograph, you can look up to the top. There's one of the wash water pipes. It was painted green, but it looks red from all of the rust. And right down on the right-hand side there, you'll see a boiler. And that's probably one of the causes of all the corrosion. Lots of heat puts lots of moisture in the air, and they don't really have HVAC to handle that. So those pipes up there are standard steel pipes that are coated, and they're still rusting to beat the band. So another issue over to the right, you see that hole in the floor, you see everybody's feet around it. That's the access to the tunnels. That's how you get equipment down there. That's how you get people down there. That's how you get materials down there. So very limited access. And we have limited access to the pipes. So the picture here is actually one of the better locations, but some of these pipes are 30 feet up, and you look up there and you wonder, which pipe is it up there that we're actually working on? And it's behind 2 or 3 others, and there's conduits going over them, and there's steam pipes running and all sorts of process pipes, and it's just difficult to get at. I say no to as-builts. There actually were as-builts, but they were schematic only. So it would show, here's the tunnel, and then just lines saying, we got this pipe, we got this pipe, we got this pipe. But where they are, you don't have a good picture of it. So that was one of the big challenges of the project. Okay. So in the pre-design, we did this with charrettes. And we had 2 charrettes. And the thought is, okay, do we rehabilitate that pipe or do we put it in a new location? Again, you can see how corroded that pipe is. And you can see that pipe right there is about 30 feet up, because you can see way down in the left corner where the floor actually is. And off to the right here is above grade, and the tunnels are right below that. So I'm going to walk through the charrettes just a little bit. Go ahead. So first charrette. So we had about 20 or 30 people from BES, and they were from every aspect of BES operations. And I will say that we did this in a very specific fashion. We didn't just have a room with 30 people and everybody talks or they don't talk like you're in a schoolroom. Because usually when you do that, there's a couple people that tend to take over the discussion. So we sat in a circle and very specifically went around to every single person. And when they were talking, there was no crosstalk. We just wanted to hear their ideas, their thoughts. We went all the way around that fashion. And we also went down to the tunnels. And we came up with all sorts of options as to what could we do. And I've listed some of them here. Build another trench in the bottom of the tunnel and put the pipe there. Put the pipe up above grade. Put it in the existing location, find new locations in the tunnels. And we even talked about totally relocating to different tunnels. CIPP lining, recoating the exterior. And by the end of this charrette, we had honed that down to these 3 options. Rehabilitate the pipe inside and outside. So coat the outside, line the inside, find a new location, or put it in the existing location. So if you look at the center photo here, you can see how jam-packed those tunnels are with other process pipe, steam pipe, conduits, equipment, electrical panels, just jammed. And we actually found some places we thought were pretty good to put the new pipe. And that's when we found out that those spaces were already spoken for. There was a big upgrade coming that wanted to use some of those spaces for rather large pipes. And a lot of the open spaces were what the ops people used with scissor lifts to get up to the pipes, because there's no walkway. Well, very few walkways. You can see there one walkway there in the center, but it only goes about 15 feet. So most of the tunnel, you don't have access. So in the end, through this charrette, we actually had done evaluation of all of these options, had the pros and cons, the costs, and through the second charrette, we did the same thing, went around the room, actually went back down to the tunnels, came back up, and by the end of the charrette, we selected an option, which was replace in place, cost estimate. So this is about 600 feet of pipe, $3.8 million. A lot of that is because of risk, because of unknowns, because of poor access. And then we also found out that the project was too large for the small project budget that BES had. So we got the project to 30% design and stopped. And then they had to put this project into their CIP budget and list, and it came out several years later. But all along, we've been talking to BES about all the unknowns and all the risks that were entailed in those unknowns, and that they probably were going to have lots of change orders because it was going to be hard to address those risks within a design set. So we started talking about alternative delivery methods. So why? Well, the as-built were only schematic. They didn't show you. I mean, you look at these pictures and look at all the pipes, look at all the odd fittings and configurations and everything that's running all over the place. You can't show that in a set of plans, and the as-built didn't show them. BES had done a survey, but it was only of the pipe we were going to replace. So it didn't show anything else. And there was a reluctance to do a 3D survey. You can do an internal LiDAR. BES had tried that on another project and didn't like the results, so they didn't want to try to do that on this project. So this was going to be difficult to show to a contractor. Go ahead. So this is also really complex. So here's just some other photos showing what's going on. The photo on the top right, look at all the pipes there. And on the bottom right, that's our access through one of the other tunnels. So very limited access. And then you look in the center here, and there's all sorts of electrical panels and pumps and other equipment directly below the pipes we have to replace that are heavy pipes. We got to take them out. Potential for dust coming down and plugging up and causing problems to the electrical panels, even to the pumps, or potentially even dropping something. So very complex, no good way to show the design. In our 30%, we added photographs actually to the design plans to try to give the contractor a feel for what they're walking into. Lots of constructability risks. You can see in the upper right that the pipes aren't all just straight. There was odd angles, and pipes were diving in and out of other pipes. So how do you show that? And what condition is that pipe really in? Can we actually get to it? So there was a high chance of change orders. And one of the reasons that our cost estimate was as high as it was is because of the unknowns and because of the risks. We didn't even know if all the valves on those pipes worked. BES was pretty sure some of them didn't work, but they didn't know which ones. That's something that we figured out through the project. So we started looking at alternative delivery methods because of the risks and the unknowns. So I'm not going to go through the standard, here's the options. I'll talk about the two main ones we looked at And I know there's all sorts of modifications and different ways of doing CMGC and design build. There's progressive design build. There's the Portland method of CMGC, and there's all sorts of different ways to structure those. But I'm going to talk about them in general and talk about what we really were considering. Now, one of the things that is often put forth is you see these, there's discussions that have been done comparing alternative delivery methods with design bid build. Personally, when I look at those, there's two things that pop out to me. One, a lot of it is theoretical, and two, a lot of it seems to be aimed at convincing folks to do alternative methods, because they tend to say why design bid build is not good and the other ones are good. But from my perspective, there's places for each. And there's places where some of them shine and other ones don't. So some of the, just real briefly, CMGC, you hire an engineer, they start along in design, and somewhere in design, 30% or 60%, you hire a contractor who then becomes part of the design team, adding that constructability element. And near the end, they give you a guaranteed maximum price. And I think that's a little deceiving, because it actually is not your maximum price. If there's changes during construction, change of conditions, you're going to get change orders. You're probably going to reduce them because you have the constructability addressed already, but there still will be change orders. And once you get to construction, everybody returns to their usual role. The owner, the engineer, and the contractor are working just like they would in a design bid build. The engineer works for the client. The client actually has higher involvement, so as compared to design bid build. So you just need to know that. It's not like, hey, we do this and we can hand it off. It's, we do this and we probably need to put more effort into it. Now, two of the reasons that people often look at alternate delivery is, hey, we can save time and cost. And I was looking at a recent study that looked at a bunch of alternate delivery projects. And what they found on average is that CMGC saved you about 1.5% on cost and about 5% on time. So that's average, and averages can be deceiving. You can have projects that save you big on cost and time, but on average, not a lot. So just something to keep in mind, that that's probably not the big reason to use alternative delivery. It does lower constructability risk, and it is good when there's high dollar amounts tied to that risk, which is what we were looking at. So next. 100.
I'm seeing the next slide. Are you not seeing it?
Yeah, just popped up. Okay, so design builds. You can do design build anywhere from 5 to 90% design. I've seen both. We were at about 30% design. So you hire the contractor team to finish the design and then do the project. So one of the big issues on this is the engineer is now working for the contractor, not for the client. Now there's probably ways to get around that, but that's the standard. And it can work really well. It did on this project. RSCI and Tetra Tech have worked on probably over a dozen projects, design build together. And so there was respect between the two firms and teamwork, and it worked really well. I have seen on other projects where the contractor has used the engineer more as somebody to justify what the contractor wants to do on the project. And then it can get a little bit difficult and challenging. So that's one of the risks going to design build, is that the engineer is now working for the contractor. Agency considerations. So this is review agencies. There are some that are fine with design build and some that aren't, and some that it's region by region. There was a project that I know of that was a wastewater project. It was over in Eastern Oregon, and the DEQ said, design build, fine, but we want to see 100% design before you start construction, which kind of defeats the purpose, or one of the purposes, of design build. So that's a consideration. On average, the study I saw said no cost savings and only maybe 1% savings on time. Now, I think there's ways to do that a little better, but you have to specifically aim at it, and you have more flexibility to do that. And on this project, we did some things for both cost and time savings that worked out. But on average, it's not a lot of difference from design, bid, build. The agency does lose some control of design because, again, the engineer is now working for the contractor. There is a reduction of competition. There's not as many design build contractors out there. There is also a reduction of constructability risks, big time. And this is good when there's lots of construction unknowns or constructability risks. Now, initially, BES was leaning towards the CMGC. In the end, they decided to go design build. So go ahead, go to the next one.
Hey, Gordon, before you move off of that comparison discussion, it looks like Sheila has a comment and question that at Beaverton, they have an engineer under the city for CMGC, and she's guessing that that can be set up per the owner's desire and team strategy.
Yeah, like I said, there's various different ways to set these up, and some of them put the engineer under the owner, and some of them don't, but it's something to consider when you're looking at the alternative delivery. How are you structuring that? So and there's ways to work with that. So I'm not saying this is the only way, but it raises the question. And so it's a question that you just need to address when you're looking at alternative delivery.
Great, thanks, Gordon.
So they did decide to do design build, and we actually teamed up with RSCI to submit on this. In the meantime, they had another on-call team that put together the actual design build documents. So we were not part of putting those documents together. So we were authorized to be on a team. And they expanded the project. They added some hypochlorite pipe replacement and increased, just about doubled the wash water length to 1,250 feet. We teamed with RSCI. Now, this was the first design build project for the BES treatment plant side. And what I would say is their design build document was aimed more at design bid build, because their requirement for the design was incredibly detailed. Maybe even more detailed than what we would have done as a regular design bid build. But the detail they wanted was amazing. And it kind of defeated the purpose a little bit of design build. But RSCI and Tetra Tech worked together and came up with a modified approach that gave BES what they wanted, but in a different fashion. And Hunter will get into that in a little bit more. But we split some of the requirements between the contractor and Tetra Tech. We also identified some opportunities that BES hadn't thought about. And the actual bid was 3.7 million. Now, that's incredibly close to what we said it was going to cost, but obviously there's more pipe. And so what this is showing is that this project had so many unknowns and risks that as an engineer, we had to pump up the cost to try to cover those. And then once we teamed up with the contractor, we could work through a bunch of that and reduce the cost. So that is one of the positives of doing design build, is you can address all those unknowns because now you have both the designer and contractor working together to put this bid together. And they both have strengths, and you put them together and you get a better project. So with that, I think I'll turn it over to Hunter to talk a little bit more about design and construction. It looks like
Thanks, Gordon.
more chat.
I mean, we've got another Q&A. Did the contractor have PEs or an in-house engineering staff that worked on the pre-design bid during this process? I would say no, they did not have engineers working for them. I guess we were fulfilling that role.
Right, and they weren't actually doing the pre-design. That's why our costs had to include potential unknowns and risks. They
right.
all during the bid, and we were the engineers, they were the contractors. They didn't have engineers on their staff.
Right, and they only got involved essentially after the 60% documents were prepared and design bids were being submitted to the city. Is that correct, Gordon?
Yeah, pretty much. We were working with them through the bid, batting back and forth ideas and design issues and construction issues. And they started working with us when we moved the documents past 30% and into finalized documents, which actually are not as comprehensive as a design bid build project, because they're sitting right there and they'll tell you, well, I don't need that detail, I don't need that information, but I do need this. And so it's much more focused on what they actually need. So.
Okay, so thanks, Gordon. As Gordon mentioned, I'm going to be talking about the design and construction phases of this project, and I'm going to be jumping around a little to focus on some of the areas where we felt the design bid delivery method really had benefits and changed the way we would have done some of these portions of the project. So starting with initial challenges, Gordon already mentioned the lack of survey data. The city had done one survey down in the tunnels, but the information was pretty patchy. It was basically center line of pipes and a few pipe invert elevations. And you saw some of those photos earlier. There is a lot crammed into those tunnels, and without a 3D view, it's pretty difficult to do a detailed design. So what we ended up doing is dividing the responsibility on the drawings. So on the left, you see what Tetra Tech put together, which was sort of a big picture schematic design that shows the proposed pipes as single line entities with the location of fittings, and then RSCI generated a 3D model only of the proposed pipe work that shows all of the fittings and bends necessary to put this all together. And it's worth pointing out that this is something that RSCI would have had to do anyway, because they need to figure out how to fabricate all these custom fittings and the pipe lengths. But because we were doing it design bid, we were able to take advantage of those drawings and do it as a collaborative process where we could look at what they were putting together and use that to modify our drawings and vice versa.
So Hunter, one of the other nice things about that is typically we'd put together our drawings, and then once a contractor is selected, they put together their drawings. We were doing this side by side, so it saves some time.
Sure. And another area that we needed to save time was on permitting. We didn't have a lot of permits for this project, but one that we needed was the City of Portland Building Department to approve our pipe supports. And because of time constraints, that other big upgrade was coming to those tunnels, and we needed to finish this project. We didn't have time to finalize our drawings, get them reviewed, and then start construction. So the plan we developed was to put together a more limited permit set focusing just on the pipe supports, get that in for review, and then complete the remainder of the design. Because we were doing these drawings early, we needed to provide a pretty comprehensive menu of options, basically every kind of pipe support we thought they might need. And we were also able to go into greater depth on the design because we were able to work with the contractor and provide details like the exact type of bolts that were going to be used, the embedment depth, things that we wouldn't necessarily put on a typical detail. Often we would say per manufacturer's requirements. So we were really able to get detailed, and that both helped with the review process and helped once it was under construction. And this sort of menu approach was helpful during construction because there was a case where I got called out. The contractor said, oh, we can't use any of our typical details for this particular location. A different pipe is in the way. And by going through these 4 pages of details, we were actually able to find one that worked. It wasn't one they'd looked at because they weren't using it anywhere else. But by having that long list of options, we were really able to help them, and their knowledge helped us put these together. Now, the pipe material that was selected by RSCI was stainless steel. The 60% documents allowed for either ductile iron or stainless steel. We would have typically assumed ductile iron because it's more commonly used and it's typically cheaper. But RSCI wanted to use stainless steel. It's a thinner wall, so it's lighter. And these tunnels are actually not a good example, but there are cases where they need to get this 30 feet up in the air. So a lighter pipe that's easier to work with has some significant benefits. And also you can custom fabricate unusual fittings, which was required in a lot of locations. You can see here a location where they're bending both vertically and horizontally with very tight requirements. So because they actually fabricated all of these fittings in Idaho, where their headquarters are located, and shipped them out to Portland. And these other two photos just show pipes in the tunnels ready to be assembled. And this fabrication process allowed us to work with some of the really difficult locations. This is a location, a room at the end of one of the tunnels, a pump room. You can see this is the pipe coming in from the tunnel. It rises up, it splits into different sized pipes. You got valves, there's another pipe coming off the top, there's one coming off the side. During construction, this got nicknamed the octopus. I don't know that it actually has 8 legs exactly, but it is a very complicated piece of assembly. This is the detailed drawing that RSCI put together to figure out just how it would be fabricated. And then they fabricated it in Idaho, they shipped it out, and they assembled it in place. Here you can see it installed. It's a lot cleaner, both literally because it's not a rusty mess, and they were just able to simplify some of these bends. I mean, the original was, you can see, also welded together, but this stainless steel version is a lot lighter, so it was both easier to assemble at the time, and if they need to do future work on it, it'll be easier then as well. For the hypochlorite transfer piping, HDPE, high density polyethylene, was selected during the 60% design. Here you can see a couple of, these are the existing PVC transfer pipes, and here are the new HDPE double contained. The reasoning behind HDPE is just that you have fusion welded joints rather than glued joints, which is typically where these PVC pipes start to fail and leak.
Hey, Hunter.
Yes.
We got a question here, so
Okay.
I'll just jump in. It says, what was the reason for the corrosion? Was it poor pipe material or the environment the pipes were in? So it was really the environment. The pipe material was pretty standard steel pipe that's coated. That's used all the time in wastewater treatment plants. But we had those boilers down there that had a lot of heat, and there was a lot of moisture in the air. And I don't think that, I'm pretty darn sure, that they didn't have appropriate HVAC to deal with all of that moisture that was being put in the air. And so I think it was environmental, because you see steel pipe, coated steel pipe used all the time.
Yeah, I agree. I mean, some of these tunnels had standing water in them, so they were almost more akin to a pump station environment than a treatment plant environment in some respects. So I definitely think it was the environment, and also the age. Some of these pipes were installed in the mid 70s when this portion of the plant was expanded. So that's a long time for a steel pipe to be in operation in a corrosive environment. So here I'm just showing some photos of different configurations of pipe supports that were installed. On the left, you can see one that's cantilevered out from the wall and also attaches to the ceiling up above. A little further down, we've got one that just goes to the ceiling. We need these intermittently to provide lateral stability in case of an earthquake, but these ones can support the weight of the pipe. Over here, we've got a floor and wall mounted. The pipe that's being supported is this one back here. So you can see the U-bolt holding it down to this new pipe support. These pipe supports were also fabricated by RSCI in Idaho and shipped out, except for a few special cases where they had to make modifications in the field. Service lines were one of our big design and construction challenges. So these wash water pipes at this location you're seeing here, there's actually a couple of wash water pipes installed at different times. This is one, you can see the WW marking. I believe this extremely rusty one in the back is another pipe. So we had service pipes that would connect to one or both of these pipes. They're feeding yard hydrants up above, spray bars to keep down foam and process uses as well in some cases. So oftentimes they dropped down. This is the service pipe coming down on each side. They drop down to floor level to allow a person standing on the floor to operate the valve. And they were just in terrible condition. They varied a lot in size, and sometimes they would connect behind the pipe, sometimes to the underside, sometimes above it. The valves weren't always operable. In some cases, the operators did not use these much, but still wanted to maintain the ability to use them. So we had to spend quite a bit of time down in the tunnels trying to catalog all these and mark them so that the contractor could replace them. Originally, the plan was to leave the existing service piping in place and just connect it to the new pipes. This pained us on a personal level because it would have been a shame to see all this nice new pipe connecting to these visibly deteriorating service pipes. Luckily, BES was able to find some additional money to, as a change order, replace the service piping. So over on the right, this is not the exact same location, but it's nearby. You can see the new service piping, new valve, new service piping dropping down, going back up. And it looks a lot better. It's simpler. Some of these strange cross connections that just weren't necessary were able to get removed. So that was something we were able to do on kind of an ongoing basis because we were working closely with the contractor. Another area where the contractor worked closely with us to significant benefit was the staging. Obviously, this is a big treatment plant. It serves most of the city's population. It cannot be taken down. And that means the wash water system cannot be taken down either. So RCI prepared a very detailed staging plan with 12 different stages. You're seeing just 2 of them here. For each one, they identified the valves that would be closed to section off particular areas so that that portion could be replaced. They also worked with the operations team to figure out, to verify that those valves were operable and to update labels on those valves so that everyone would be working on the same playbook. And if we as the engineers had designed this plan, it would have been less detailed because we would have wanted to allow the contractor some flexibility. And we also would have assumed that bypass pumping would be required. But because we were able to work closely with the contractor and develop this plan, the contractor and the client, we were able to avoid any bypass pumping and just replace it section by section. And this plan worked really well. I think they had to make a couple of minor modifications due to valve issues, but they were able to keep the whole system live the whole time.
Hunter, so just to add her on to that, this is probably one of the places that saved the project a lot of money, because when we originally put together the pre-design, we assumed that they were going to essentially put in the pipe twice, once as essentially the bypass, lay some pipe on the ground and reattach it somewhere, and then build the pipe. But because we were working with the contractor and they know, hey, we can build this and here's where we can stop and here's where we can do certain things to keep this other pipe running, we were able to essentially jettison all bypass piping. So again, one of the benefits of having the contractor and the engineer working together.
Yes, absolutely. Over on the hypochlorite system side, which is something we're covering less in this presentation, but it was an important element of the project. I already talked about the pipe material being HDPE. Design considerations for this, it needed to slope down to drain points. You can see one here, a newly constructed one. We also needed to locate these at existing floor drains, of which there are surprisingly few in these tunnels. Part of the reason why there's standing water in a couple locations. And we also needed to slope up to air release valves to release air that builds up in the lines. And you can see new pipe installed here next to existing pipe, or that may actually be conduit above it. But I'm going to come back to the air release valves because that's an issue that came up during construction. Another element that came up during construction and we were able to work through as a team, the existing system had a small surge tank located at the top of that octopus fitting. You can see it here behind that valve. The original plan was just to replace it in kind, but we didn't have any real design information for that surge tank, and BES didn't have a model for their pipe network. So it was hard for the contractor to size this thing, and it was hard for us to give them any sizing information. So we were able to do some additional modeling during construction, and we determined that to prevent surge issues when a valve closes or a pump shuts down, we needed to add a slightly larger surge tank, which got moved down to the floor. So you can see that here. It's essentially located below this fitting. And here it is painted and connected up to the system.
And they actually did have surge problems back in their history. I think they blew out 2 PVC pipes prior to this. So everybody knew it was an issue, but we didn't have the information to say how big of an issue. So the modeling was incredibly helpful.
Yeah, definitely. Now, during the construction process, BES provided a full-time inspector. Tetra Tech was on site when requested by the contractor. If they encountered an issue, we would come out and take a look at it with them and brainstorm solutions. And it was nice to be operating in this kind of approach. Sometimes when an engineer is on site with the contractor, you can have a bit of an adversarial role where they feel like you're looking over their shoulder for problems, and you as the engineer might feel like they're trying to conceal any problems. In this case, since we were on the same team, both working to give BES the best product possible, we were able to really work together. They could tell us the constraints they had, and we could work together to find solutions. Oftentimes we'd provide a sketch if there was a difficult pipe support, something like that. We also provided review during the design process because, again, we're on the same team. They were able to start submitting their proposed materials and valves, et cetera, while we were still working on design. And that was extremely useful, both because then we could base design around the products they planned to use, and because it sped up the process. And as I mentioned, that was important to BES to get this done ahead of planned additional work in these tunnels. And during construction, we were able to work as a collaborative problem-solving team, us, the engineers, and the contractor and the owner, because their inspector was there all the time and also had a lot of good ideas. So I'm just going to cover a couple of the kind of problems that came up during construction, not even problems, but questions that we were able to work through together. So the first is those hypochlorite air release valves. These need to be at high points in the system. And the original plan, so this junction of 2 tunnels, it was originally planned to put an air release valve up in this vicinity. And the idea was we were going to cut a hole in this deck, which is the walkway up above and the roof of the tunnel, so that an operator could reach down and operate the air release valve manually. The problem is that was going to be a significant reach down. I forget the exact distance, but it was at least 2 or 3 feet. And there at that point suspended 30 feet above the floor of this tunnel. So that's potentially dangerous. They, I would assume, need to be harnessed in. It's going to be a hassle to operate that. So the city asked us to put in a platform instead. You see here one of their existing platforms with a built-in ladder. So the idea was we'd have a dedicated platform for each of these valves. There were 2 in this area. But you can see how much is in these tunnels and how difficult it would be to locate a new platform. And we started to develop a couple locations for those platforms, but by working together, we came to a simpler solution, which was the contractor took the money that it would have cost them to build these platforms, and they bought the city a new compact scissor lift that would fit in the locations we put these valves so that they can get at them when they need to get at them, and then move that scissor lift out of the way when they don't need to get at them, because it's a relatively infrequent need to access these. So that ended up saving everyone money, and it kept the tunnels as clear as possible of new pipes and infrastructure, because there's more infrastructure coming. Another item that came up was air in the hypochlorite lines. This is a location where we are feeding these pumps from a bulk tank that's across this wall. And we replaced the existing system basically at the same location, same pipe sizes, same valves, just HDP instead of PVC. But they'd never had air in these lines, and suddenly they were getting just ferocious foaming in these calibration columns. I went to observe it, and it would foam for 3 or 4 minutes when they first turned it on in the morning. There was a lot of air in this line. And we ended up adding some air release valves, both at these elbows coming down that feed each pump, and also one coming out of the bulk tank. And the conclusion was the old PVC pipes had enough gaps in the joints that it was just able to release some of that air, and the new tighter HDPE lines were not releasing that air, and suddenly it was trapped in the line. And we were able to, again, work collaboratively on that. The contractor could honestly share the constructability issues they saw with making those replacements. And as a team, we, DES, and the contractor were able to work together and just figure out a good place to add those additional valves, 5 additional valves, which then corrected the problem. And then finally, on record drawings, the primary record drawings were our design drawings. So it was those single line schematic drawings. And then in locations where additional work was done, the contractor also provided photos and markups that were added as appendix sheets to the drawing set. You can see an example here where they did some additional work at hypochlorite feed points. So they did not update their shop drawings, although their shop drawings didn't change much. In general, the things that changed were just additional work on places like the service lines and some additional valves. So that brings me to the end. This was a good project for us and for everyone else involved. And we think it was a really good application for the design build approach, because as I kept saying, we were able to work as a collaborative team. Obviously, that's something you try and do in a design bid build process as well, but it's a little simpler with this delivery method. And in this case, it worked really well. So if anyone has additional questions or feel like earlier questions need more discussion, we're here.
I'll just add just a little bit. You know, one of the things that we were trying to get at in this presentation is, why would you do design build? And I think some of the big takeaways are, if you got a lot of risk, if you got a lot of unknowns, and one that we didn't talk about a lot, but I think is important, is that this project was actually fairly simple. We didn't have a lot of equipment. We didn't have any process. We didn't have to make things work together. We had standard pipes and valves and dealing with that. So there, from a design standpoint, it wasn't incredibly complex with regards to process or equipment. And I think that also lends itself to a design build process.
Gordon, we got a question in the Q&A about roadway design, but I think that might have been misheard. There was no roadway design involved here.
Yeah, no roadway design, but there was difficult access.
All right. Well, thank you, Gordon and Hunter. It was it sounds like a very interesting project. Those tunnels and the magnitude of work that goes and stuff in them is pretty remarkable. So thank you for the presentation, and I look forward to hearing more about what folks are doing. So feel free to reach out. Thanks, everybody.
Hey, Jennifer, there's one more question. They wanted to know if the PowerPoint would be available, and certainly, should we just send that to you and you'll post it? Is that how that goes?
Yeah, that would be fine. And what I would do is I would post it on our Lunch and Learn webpage. So if you go to the Oregon APWA website, you can look under the conferences and trainings to find our online opportunities. And that's where I've posted PowerPoints in the past when speakers have provided those.
Okay, so Hunter will send that over to you.
Great. Thank you, everybody.
Okay, I think that's a wrap.
Yes, I